Hello folks, welcome back. This is part 4, I think, of my build log of the Trumpeter 1 to 200 scale model of the Titanic. Today I'm going to talk through how I designed my rudder mechanism. And this was such a fiddly little job. Of all the things I've done so far on this kit, this was just so fiddly. It took me absolutely ages to do, but to be fair, in the end I've ended up with a really nice, solid and smooth rudder mechanism that I'm really happy with. So I'm going to kick off the video by talking through how I arrived at the design that I'm going to use. The first thing I wanted to do was to work out the actual load that was going to be applied to the rudder. Now there's quite a few different equations for doing this, and actually it gets quite involved quite quickly. You can start to look at things like the aerofoil of the rudder and vectors associated with that, and you can look at the coefficient of friction between the rudder and the water flowing across it. But to be quite honest, for the sake of a model boat, I don't think that's necessary. It's probably necessary on a full-size ship, but for a model boat I think that's massively overkill. So what I decided to do instead was to sort of dumb down the equation and simply work out the amount of water that's going to flow over the rudder per second. So to do this I used CAD to work out the surface area of the rudder when the rudder's at full lock, i.e. the ship is turning as much as it possibly could. And I worked out this area in meters squared. Once I'd done this, I also used the speed of the ship when travelling at full velocity. And multiplying these two numbers together allowed me to work out the volume of water that's going to flow over the rudder per second. Once I had the volume, I could use the equation density equals mass divided by volume to work out the mass of water that's going to flow over the rudder per second. And that mass is essentially equal to the force, i.e. it's the maximum load that the rudder is ever going to see. Now this, to be honest, was a fairly long-winded way of finding out something that I was already pretty confident in, that all of these calculations proved that the rudder was going to be more than strong enough to deal with the instantaneous loads that it's going to experience. But what I was more worried about was the effects of secular loading on this rudder. As you can see, the plastic brackets that hold the rudder in place are really small, and I was worried about the effects of repeated force upon these, because I was worried that over time these brackets will wear, and as they wear the rudder's going to develop play, and you end up in a bit of a vicious circle where the more wear you have, the more play the rudder has, and the more play that the rudder has will increase the wear on the rudder, and so on and so on and so on. So the upshot of all this maths was I concluded that in order to have an effective rudder mechanism I would need to do something to strengthen these brackets so that they would be resistant to wear and tear caused by secular loading over time. So I went away and had a think, and I came up with an idea which is relatively hard to explain, so I've done an animation on CAD which hopefully makes it a bit easier to understand. But this idea revolves around me drilling out 0.8mm holes in all of the brackets on the hull side and all of the brackets on the rudder side. Then what I'm going to do is I'm going to insert bushings into all of these holes. These bushings are going to be made of brass. It's going to have an outside diameter of 0.8 of a mil and an inside diameter of 0.6 of a mil. So like I say, these are going to be on all of the brackets on the rudder and all of the brackets on the hull side. And the idea is that these bushings are going to provide space for a 0.5mm brass pin to pass through all of them in the hull and the rudder, which will lock the hull and the rudder together, but allow movement. So to do this job, I'm going to use a few different products. The first is this stuff. This is a hollow brass tube made by Albion Alloys. So these are a UK-based company, and they specialise in really, really fine metals for model makers, so it's absolutely ideal for the job. And this tube is has a 0.8mm outside diameter and a 0.6mm inside diameter, so it's absolutely tiddly stuff we're dealing with. And as for the securing pin, I'm going to use this stuff, and this is a 0.5mm brass rod, also from Albion Alloys. The other thing that I would recommend that you get is this. This is a Zeus guide, and I use it on pretty much any mechanical job I'm doing. But it's a really, really useful book. It's got loads of different things. It's got things like conversion tables between imperial and metric drill sizes. It's got tapping sizes for various, well, hundreds of different thread types, all that kind of stuff. It's a really useful book full of lookup tables, but the pertinent stuff today is that it also has the tolerances required for holes and shafts of different diameters. So for the rudder, I'm wanting a transition fit, which is a very close fit, but it's not an interference fit. And so this lookup table provides me for holes spaced from 0 to 3 millimeters. It gives me the tolerances that I need to apply for my bearings and pin. And that's how I've spec'd the brass metal that I'm using today. There's 3 reasons why I've chosen to use brass here. The first is that there's going to be a lot less friction, brass on brass, than there would be plastic on plastic, which is going to reduce wear overall. Second reason is that brass is significantly harder wearing than plastic, so even with increased wear, brass is going to do a much better job. The third reason, and perhaps the most important reason, is because this allows an element of replaceability. If after 2 years running I find that these bearings are actually wearing quite badly, I can simply remove the brass bushings and replace them with fresh ones. Whereas if I use the plastic, which is connected directly to the hull, I don't have that option. So without any further ado, I'm going to show you how I installed it. So I started out by drilling the holes that I could easily access with a 0.8mm drill bit, as you can see here. As you can see though, very quickly I ran out of length on the drill bit, so what I did was I heated one of my 0.5mm brass rods to quite a high temperature and then hammered down the end and sharpened the end to make my own sort of custom drill bit. might remember in the last episode I had to cut off the bottom brackets of the rudder mount to allow me to drill out the central propeller shaft. In this clip what I'm doing is I'm adding some pins into the hull of the ship so that I can connect this piece back on more securely. This is going to give me a mechanical bond, and once I've glued it, also a chemical bond. And so here is the part being glued back in place. I secured it just with some tape, and it took quite a long time to make sure it was all true. There was quite a lot of sort of tapping with a small hammer and stuff to make sure that it was actually in the correct place. But once it glued down, it was fine. This is the final position of the rudder. I decided to take off the plastic nubs on the top of the brackets. And instead I've replaced them just by extending the bushings by the same amount, about 1 millimetre. And this is meant to represent the large bolt heads which secured the rudder in place. I had a bit of a change of heart at the last minute regarding the securing pin that went through the length of the rudder, because it occurred to me that it wouldn't look as realistic if there was a large pin going up the entire length of the rudder. The Titanic didn't have that. So what I decided on doing instead is using a securing pin per bracket. So what I did was I chopped off a small length of pin and put it through each bracket in turn, and just flattened the head down enough so that the top of the pin was slightly larger than the bushing, and that would always secure it in place while still allowing free movement. So there we are, that is the rudder installed. Quite a few people have been asking me in the comments if I'm aware of the these RC conversion packs that you see on eBay, you know, where you get a brass rudder and 3 propeller shafts and so on. The answer to that is yes, I am aware of those. I'm personally not going to be using them. I haven't got anything against them or anything. I can't really comment on their quality because I've never used a kit like that before. From the pictures I've seen online, they look perfectly good. But like I say, I'm not going to use them. And the reason for that is that one of the things that I really enjoy about model building is this sort of micro-engineering, you know, the problem-solving element that comes with it. And I feel like if I bought one of these kits, I'd actually be taking away a lot of that enjoyment just by buying it. So that's my reason for not doing so. I just wanted to address that comment because it was one of the most common occurring ones in the comments down below. So that's it, the rudder's now installed. I'm really happy with how this turned out actually. It's not an easy job in the slightest. It's desperately fiddly. But it's produced a really nice solid attachment for the rudder into the hull, and it gives me a really nice smooth movement, so I'm really happy with how it's turned out. So anyway, that's it for this video. If you've enjoyed it, please like and maybe think about subscribing, and I will see you in the next one. Cheers!